contacts should have a correctly sized plastic plug installed. Drainage. Connectors must be installed in a manner that ensures moisture and fluids drain out of, and not into the connector when unmated. Wiring must be routed, so that moisture accumulated on the bundle drains away from connectors. When connectors must be mounted in a vertical position, as through a shelf or floor, the connectors must be potted or environmentally sealed. In this situation, it is better to have the receptacle face downward, so that it is less susceptible to collecting moisture when unmated. Wire support. A rear accessory back shell must be used on connectors that are not enclosed. Connectors with very small size wiring, or subject to frequent maintenance activity, or located in high vibration areas must be provided with a strain relief type back shell. The wire bundle should be protected from mechanical damage with suitable cushion material where it is secured by the clamp. Connectors that are potted, or of molded rear adapters do not normally use a separate strain relief accessory. Strain relief clamps should not impart tension on wires between the clamp and contact. Figure 9-162. Sufficient wire length must be provided at connectors to ensure a proper drip loop and that there is no strain on termination after a complete replacement of the connector and its contacts. Coaxial cable. All wiring needs to be protected from damage. However, coaxial and triaxial cables are particularly vulnerable to certain types of damage. Personnel should exercise care while handling or working around coaxial. Figure 9-163 coaxial. Figure 9-162. Backshells with strain relief. Figure 9-163. Coaxial cables. Damage can occur when clamped too tightly, or when they are bent sharply, normally at or near connectors. Damage can also be incurred during unrelated maintenance actions around the coaxial cable. Coaxial cable can be severely damaged on the inside without any evidence of damage on the outside. Coaxial cables with solid center conductors should not be used. Stranded center coaxial cables can be used as a direct replacement for solid center coaxial. Figure 9-164 coaxial cable precautions include: never kink coaxial cable, never drop anything on coaxial cable, never step on coaxial cable, never bend coaxial cable sharply, never loop coaxial cable tighter than the allowable bend radius, never pull on coaxial cable except in a straight line, never use coaxial cable for a handle, lean on it, or hang things on it, or any other wire. Wire inspection. Aircraft service imposes severe environmental condition on electrical wire. To ensure satisfactory service, inspect wire annually for abrasions, defective insulation, condition of terminations, and potential corrosion. Grounding connections for power, distribution equipment, and electromagnetic shielding must be given particular attention to ensure that electrical bonding resistance has not been significantly increased by the loosening of connections or corrosion. Electrical system components. Switches. Switches are devices that open and close circuits. They consist of one or more pair of contacts. The current in the circuit flows when the contacts are closed. Switches with 9-96. Plug straight receptacle flange mount receptacle. PNC series connectors. Plug straight receptacle flange mount receptacle. PNC series connectors. Plug straight receptacle flange mount receptacle. N series connectors. Plug straight receptacle flange mount receptacle. C series connectors. Figure 9-164. Coaxial cable connectors. Momentary contacts actuate the circuit temporarily, and they return to the normal position with an internal spring when the switch is released. Switches with continuous contacts remain in position when activated. Hazardous errors in switch operation can be avoided by logical and consistent installation. Two position on/off switches should be mounted, so that the on position is reached by an upward or forward movement of the toggle. When the switch controls movable aircraft elements, such as landing gear or flaps, the toggle should move in the same direction as the desired motion. Inadvertent operation of a switch can be prevented by mounting a suitable guard over the switch. Figure 9-165. 9-97. Figure 9-165. Switch guard. A specifically designed switch should be used in all circuits where a switch malfunction would be hazardous. Such switches are of rugged construction and have sufficient contact capacity to break, make, and carry continuously the connected load current. Snap-action design is generally preferred to obtain rapid opening and closing of contacts regardless of the speed of the operating toggle or plunger, thereby minimizing contact arcing. The nominal current rating of the conventional aircraft switch is usually stamped on the switch housing. This rating represents the continuous current rating with the contacts closed. Switches should be derated from their nominal current rating for the following types of circuits. 1. High rush-in circuits, containing incandescent lamps that can draw an initial current 15 times greater than the continuous current. Contact burning or welding may occur when the switch is closed. 2. Inductive circuits, magnetic energy stored in solenoid coils or relays is released and appears as an arc when the control switch is opened. 3. Motors, DC motors draw several times their rated current during starting, and magnetic energy stored in their armature and field coils is released when the control switch is opened. Figure 9-166 is used for selecting the proper nominal switch rating when the continuous load current is known. This selection is essentially a derating to obtain reasonable switch efficiency and service life. Haibach switches. Single pole single throw, SPST, opens and closes a single circuit. Pole indicates the number of separate circuits that can be activated, and throw indicates the number of current paths. Double pole single throw, DPST, turn two circuits on and off with one lever. Single pole double throw, SPDT, route circuit current to either of two paths. The switch is on in both positions. For example, switch turns on red lamp in one position and turns on green lamp in the other position. Double pole double throw, DPDT, activates two separate circuits at the same time. Double throw switches have either 2 or 3 positions. 2-position switch pole always connected to one of the 2 throws. 3-position switches have a center off position that disconnects the pole from both throws. Spring-loaded switches available in 2 types. 1. Normally open, no, and 2. Normally closed, NC. The contacts of the no switch are disconnected in the normal position and become closed when the switch is activated. The switch returns to the normal position when the applied force to the switch is released. The contacts of the NC switch are connected in the normal position and become open when the switch is activated. The switch returns to the normal position when the applied force to the switch is released. Toggle and rocker switches. Toggle and rocker switches control most of aircraft's electrical components. Figure 9-167 aircraft that are nominal system voltage, DC. Type of load derating factor, 28V, 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 12V, 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 12V. Lamp inductive resistive motor, lamp inductive resistive motor, 8, 4, 2, 3, 5, 2, 1, 2. Figure 9-166. Derating table for switches. 9-98. Figure 9-168. A micro switch. Figure 9-167. Toggle and rocker switches. Outfitted with a glass cockpit, often use push buttons to control electrical components. Robbery switches. Robbery switches are activated by twisting a knob or shaft and are commonly found on radio control panels. Robbery switches are utilized for controlling more than 2 circuits. Precision, micro switches. Micro switches require very little pressure to activate. These types of switches are spring-loaded. Once the pressure is removed, the contacts return to the normal position. These types of switches are typically single pole double throw, SPDT, or double pole double throw, DPDT, and have 3 contacts: normally open, normally closed, and common. Micro switches are used to detect position or to limit travel of moving parts, such as landing gear, flaps, spoilers, etc. Figure 9-168. Relays and solenoids, electromagnetic switches. Relays are used to control the flow of large currents using a small current. A low-power DC circuit is used to activate the relay and control the flow of large AC currents. They are used to switch motors and other electrical equipment on and off and to protect them from overheating. A solenoid is a special type of relay that has a moving core. The electromagnet core in the relay is fixed. Solenoids are mostly used as mechanical actuators, but can also be used for switching large currents. Relays are only used to switch currents. Solenoids. Solenoids are used as switching devices where a weight reduction can be achieved or electrical controls can be simplified. The foregoing discussion of switch ratings is generally applicable to solenoid contact ratings. Solenoids have a movable core/armature that is usually made of steel or iron, and the coil is wrapped around the armature. The solenoid has an electromagnetic tube, and the armature moves in and out of the tube. Figure 9-169. Relays. The 2 main types of relays are electromechanical and solid state. Electromechanical relays have a fixed core and a moving plate with contacts on it, while solid-state relays work similar to transistors and have no moving parts. Current flowing through the coil of an electromechanical relay creates a magnetic field that attracts a lever and changes the switch. Figure 9-169. Solenoid. 9-99. Contacts. The coil current can be on or off, so relays have 2 switch positions, and they are double-throw switches. Residual magnetism is a common problem, and the contacts may stay closed, or are opened by a slight amount of residual magnetism. A relay is an electrically operated switch, and is therefore subject to dropout under low system voltage conditions. Relays allow one circuit to switch a second circuit that can be completely separate from the first. For example, a low-voltage DC battery circuit can use a relay to switch a 110-volt 3-phase AC circuit. There is no electrical connection inside the relay between the 2 circuits. The link is magnetic and mechanical. Figure 9-170. Current limiting devices. Inductors should be protected with circuit breakers or fuses located as close as possible to the electrical power source bus. Normally, the manufacturer of the electrical equipment specifies the fuse or circuit breaker to be used when installing equipment. The circuit breaker or fuse should open the circuit before the conductor emits smoke. To accomplish this, the time current characteristic of the protection device must fall below that of the associated conductor. Circuit protector characteristics should be matched to obtain the maximum utilization of the connected equipment. Figure 9-171 shows a chart used in selecting the circuit breaker and fuse protection for copper conductors. This limited chart is applicable to a specific set of ambient temperatures and wire bundle sizes, and is presented as typical only. It is important to consult such guides before selecting a conductor for a specific purpose. For example, a wire run individually in the open air may be protected by the circuit breaker of the next higher rating to that shown on the chart. Fuses. A fuse is placed in series with the voltage source, and all current must flow through it. Figure 9-172. The fuse consists of a strip of metal that is enclosed in a glass or plastic housing. The metal strip has a low melting point and is usually made. Figure 9-170. Relay. Wire and gauge copper. Circuit breaker amperage. Fuse amperage. 22. 20. 18. 16. 14. 12. 10. 8. 6. 4. 2. 1. 0. 5. 7.5. 10. 15. 20. 30. 40. 50. 80. 100. 125. 5. 5. 10. 10. 15. 20. 30. 50. 70. 70. 100. 150. 150. Figure 9-171. Wired and circuit protection chart. Figure 9-172. A fuse. Of lead, tin, or copper. When the current exceeds the capacity of the fuse, the metal strip heats up and breaks. As a result of this, the flow of current in the circuit stops. There are two basic types of fuses: fast-acting and slow flow. The fast-acting type opens very quickly when their particular current rating is exceeded. This is important for electric devices that can quickly be destroyed when too much current flows through them for even a very small amount of time. Slow flow fuses have a coiled construction inside. They are designed to open only on a continued overload, such as a short circuit. Circuit breakers. A circuit breaker is an automatically operated electrical switch designed to protect an electrical circuit from damage caused by an overload or short circuit. Its basic function is to detect a fault condition and immediately discontinue electrical flow. Unlike a fuse that operates once and then has to be replaced, a circuit breaker can't be reset to resume normal operation. All resettable circuit breakers should open the circuit in which they are installed regardless of the position of the operating control when an overload or circuit fault exists. Such circuit breakers are referred to as trip-free. Automatic. 9-100. Reset circuit breakers automatically reset themselves. They should not be used as circuit protection devices in aircraft. When a circuit breaker trips, the electrical circuit should be checked and the fault removed before the circuit breaker is reset. Sometimes circuit breakers trip for no apparent reason, and the circuit breaker can be reset one time. If the circuit breaker trips again, there exists a circuit fault and the technician must troubleshoot the circuit before resetting the circuit breaker. Figure 9-173. Some new aircraft designs use a digital circuit protection architecture. This system monitors the amperage through a particular circuit. When the maximum amperage for that circuit is reached, the power is rerouted away from the circuit. This system reduces the use of mechanical circuit breakers. The advantages are weight savings and the reduction of mechanical parts. Aircraft lighting systems. Aircraft lighting systems provide illumination for both exterior and interior use. Lights on the exterior provide illumination for such operations as landing at night, inspection of icing conditions, and safety from mid-air collision. Interior lighting provides illumination for instruments, cockpits, cabins, and other sections occupied by crew members and passengers. Certain special lights, such as indicator and warning lights, indicate the operation status of equipment. Exterior lights. Position, anti-collision, landing, and taxi lights are common examples of aircraft exterior lights. Some lights are required for night operations. Other types of exterior lights, such as wing inspection lights, are of great benefit for specialized flying operations. Position lights. Aircraft operating at night must be equipped with position lights that meet the minimum requirements specified by Title 14 of the Code of Federal Regulations. A set of position lights consists of one red, one green, and one white light. Figures 9-174 and 9-175. On some types of installations, a switch in the cockpit provides for steady or flashing operation of the position lights. On many aircraft, each light unit contains a single lamp mounted on the surface of the aircraft. Other types of position light units contain two lamps and are often streamlined into the surface of the aircraft structure. The green light unit is always mounted at the extreme tip of the right wing. The red unit is mounted in a similar position on the left wing. Figure 9-174. A left wing tip position light, red, and a white strobe light. Figure 9-173. Circuit breaker panel. Figure 9-175. A right wing tip position light, also known as an aviation light. 9-101. Light unit is usually located on the vertical stabilizer in a position where it is clearly visible through a wide angle from the rear of the aircraft. Figure 9-176 illustrates a schematic diagram of a position light circuit. Position lights are also known as navigation lights. There are, of course, many variations in the position light circuits used on different aircraft. All circuits are protected by fuses or circuit breakers, and many circuits include flashing and dimming equipment. Small aircraft are usually equipped with a simplified control switch and circuitry. In some cases, one control knob or switch is used to turn on several sets of lights. For example, one type utilizes a control knob, the first movement of which turns on the position lights and the instrument panel lights. Further rotation of the control knob increases the intensity of only the panel lights. A flasher unit is seldom included in the position light circuitry of very light aircraft, but is used in small twin-engine aircraft. Traditional position lights use incandescent light bulbs. LED lights have been introduced on modern aircraft because of their good visibility, high reliability, and low power consumption. Anti-collision lights. An anti-collision light system may consist of one or more lights. They are rotating beam lights that are usually installed on top of the fuselage or tail in such a location that the light does not affect the vision of the crew member or detract from the visibility of the position lights. Large transport-type aircraft use an anti-collision light on top and one on the bottom. Figure 9-177. Anti-collision lights of the aircraft. Figure 9-177 shows a typical anti-collision light installation in a vertical stabilizer. WG STA 124.6, J282 P282, L168 A20, A223 panel assembly sub-panel, LINPD, 25-53-02, W159, 5A, CB121, nav light, H91-29, L168 P20, nav light PWR20 DS104/XDS104, R nav light, G ground 20, L168 D20, P238 J238, I, red DS103/XDS103, tail nav light, CBLK, WG STA 124.6, J281 P281, I, P239 J239, L178 20 NGS 129 33-47, L168 F20, H91-28, L168 G20, nav light PWR 20 DS104/XDS104, L nav light, R ground 20, figure 9-176, navigation light system schematic, 9-102. An anti-collision light unit usually consists of one or two rotating lights operated by an electric motor. The light may be fixed, but mounted under rotating mirrors inside a protruding red glass housing. The mirrors rotate in an arc, and the resulting flash rate is between 40 and 100 cycles per minute. Newer aircraft designs use a LED type of anti-collision light. The anti-collision light is a safety light to warn other aircraft, especially in congested areas. A white strobe light is a second type of anti-collision light that is also common. Usually mounted at the wingtips and, possibly, at empennage extremities, strobe lights produce an extremely bright intermittent flash of white light that is highly visible. The light is produced by a high-voltage discharge of a capacitor. A dedicated power pack houses the capacitor and supplies voltage to a sealed xenon-filled tube. The xenon ionizes with a flash when the voltage is applied. A strobe light is shown in figure 9-174. Landing and taxi lights. Landing lights are installed in aircraft to illuminate runways during night landings. These lights are very powerful and are directed by a parabolic reflector at an angle providing a maximum range of illumination. Landing lights of smaller aircraft are usually located midway in the leading edge of each wing or streamlined into the aircraft surface. Landing lights for larger transport category aircraft are usually located in the leading edge of the wing close to the fuselage. Each light may be controlled by a relay, or it may be connected directly into the electric circuit. On some aircraft, the landing light is mounted in the same area with a taxi light. Figure 9-178 a sealed beam, halogen, or high-intensity xenon discharge lamp is used. Taxi lights are designed to provide illumination on the ground, while taxiing or towing the aircraft to or from a runway, taxi, strip, or in the hangar area. Figure 9-179 taxi lights are not designed to provide the degree of illumination necessary for landing lights. On aircraft with tricycle landing gear, either single or multiple taxi lights are often mounted on the non-steerable part of the nose landing gear. They are positioned at an oblique angle to the center line of the aircraft to provide illumination directly in front of the aircraft, and also some illumination to the right and left of the aircraft's path. On some aircraft, the dual taxi lights are supplemented by wingtip clearance lights controlled by the same circuitry. Taxi lights are also mounted in the recessed areas of the wing leading edge, often in the same area with a fixed landing light. Many small aircraft are not equipped with any type of taxi light, but rely on the intermittent use of a landing light tube. Figure 9-178. Landing lights. Figure 9-179. Taxi lights. 9-103. Illuminate taxiing operations. Still other aircraft utilize a dimming resistor in the landing light circuit to provide reduced illumination for taxiing. A typical circuit for taxi lights is shown in Figure 9-180. Some large aircraft are equipped with alternate taxi lights located on the lower surface of the aircraft, aft of the nose radome. These lights, operated by a separate switch from the main taxi lights, illuminate the area immediately in front of and below the aircraft nose. Wing inspection lights. Some aircraft are equipped with wing inspection lights to illuminate the leading edge of the wings to permit observation of icing and general condition of these areas in flight. These lights permit visual detection of ice formation on wing leading edges, while flying at night. They are usually controlled through a relay by an on/off toggle switch in the cockpit. Some wing inspection light systems may include, or be supplemented by additional lights, sometimes called nacelle lights, that illuminate adjacent areas, such as cowl flaps or the landing gear. These are normally the same type of lights, and can be controlled by the same circuits. Interior lights. Aircraft are equipped with interior lights to illuminate the cabin. Figure 9-181 often white and red light settings are provided. Commercial aircraft have a lighting systems that illuminates the main cabin, an independent lighting system so that passengers can read when the cabin lights are off, and an emergency lighting system on the floor of the aircraft to aid passengers of the aircraft during an emergency. Figure 9-181. Interior cockpit and cabin light system. TB102. 24-53-02. W159. L178A16. L176B18. CL177A18N. DS110. XDS110. Right landing light. L178B16. CL179A16N. DS106. XDS106. Taxi light. 5. L178A16. CR127. CR217. 15A. CB121. Taxi light. 10A. CB178. R landing light. 5. 4. S104-4-20. 6. 32-61. S104 nose gear up lock switch. CR126. L173B18. CL174A18N. DS109. XDS109. Left landing light. 3. L173A18. 24-53-01. W119. NA. CB177. L landing light. 1. A223 panel ASI, sub-panel, L inboard. L382231-51-04. 32-61. Figure 9-180. Taxi light circuit. 9-104. Maintenance and inspection of lighting systems. Inspection of an aircraft's lighting system normally includes checking the condition and security of all visible wiring, connections, terminals, fuses, and switches. A continuity lighter meter can be used in making these checks, since the cause of many troubles can often be located by systematically testing each circuit for continuity. 9-105. 9-106. Glossary.